All right, this video is going to be addressing two different learning targets. Learning target 3 is writing an equation in slope-intercept form. And learning target 4 is explaining the different pieces of the equation and how they're evident in different forms. So we're going to have to explain the different pieces, okay? So actually this time we're going to start off with an example and then we're going to go back and define a couple things. I want to show you kind of where that equation comes from, that slope-intercept form equation that you might have heard of before. So we're going to talk about an example first. So the example is about a minivan that's 220 miles from its destination of Flint. Flint's just a town name. And it begins traveling towards Flint at 72 miles an hour. So we're going to go ahead and write a recursive routine. You've been doing this for a little while now. We have to, of course, do our start. Our start value in this case is 220. We're starting 220 miles away from the destination. And as we go, the next thing that's going to happen is that we'll take our previous location and we're going to subtract 72 for every hour because we're traveling closer, so our distance is actually going to be 72 less every hour. Okay? So I've got my recursive routine here, and it says write an expression to find the distance after 3 hours. And I want to show you how this works with a recursive routine so that I can hopefully shed some light for you about how this relates to a slope-intercept form. So we've got our distance over hours, okay? And then I'm going to write expressions for each of these. Okay, so distance at 0 hours, let's flip those around, I'm sorry. All right, at 0 hours, we are at 220. So that's just starting value at 220. There's really no expression that we can do for that. We haven't done any work yet. After 1 hour, we're 148 miles away, and how I got that was I took 220 and I subtracted 72, okay, for the 1 hour. After 2 hours, I'm going to be at 76 miles away, right? So 148 minus 72 was 76. And if I just keep everything the same, it's actually our distance subtracted 72 twice, okay, because we've traveled 2 hours, so we subtracted 72 and subtracted another 72. And then in the third hour, we're going to be at 4 because we're going to be 4 miles away because we've taken 220 and we've subtracted 72 3 times. Okay, that's how a recursive routine works. You need the previous term to get to where you want to go. And what I want to show you is how we can take this and make it more simple so that we just know after a certain number of hours. Okay? And so what I notice is that after 3 hours, there's 4 left because I've subtracted 72 3 times. After 2 hours, there's 76 miles left because I've subtracted 72 twice. So what I notice is that I'm going to subtract the number of times for the number of hours that I've been traveling. Subtract 72 3 times for 3 hours, twice for 2 hours. So what I want to do is I want to actually define some variables here. So I actually want to call my variables hours and distance, okay? Hours and distance. And I want to write an expression that helps me so that I don't have to start back at 220 every time, okay? So how this is going to work is we're going to find the distance. And so I'm going to write D equals, by doing this, by taking this expression, 220, and subtracting 72 times the number of hours. So rather than thinking of it minus 72, minus 72, minus 72, it's just really 220 minus 72 times 3. Okay? It's really just subtracting it that many times, 3 times. So I can take it times the number of hours. Okay? So let me show you how that works with the rest of our problem here. Defining variables, I'm actually going to use an x and a y this time. H and D are fine and good, but when we're writing equations in slope-intercept form, we're going to actually use x and y so that when we go to graph it, we know which one goes where. So I'm going to use x for hours, and I'll talk to you in a minute here about how I knew which one to put it for. And I'm going to use y for distance. And I'm going to put it in a different order here. I'm going to write y equals negative 72x plus 220. That's actually our equation, and I'm going to I hope that you understand a little bit now more about how that shows the van's distance from Flint, but I just want to talk a little bit about how we got each of those and how they show up in the recursive routine and in the equation, and then also how it's going to show up in the graph, okay? And then we'll go ahead and define those terms for you. So the starting value and the rule, okay, so the starting value of 220 and the rule of negative 72 minus 72, okay? How do they show up in the equation? Okay, so in the equation, the rule shows up as our coefficient. We learned about this term, I think, last unit. It's that number that's with the variable, okay? And our starting value, our start, shows up in the equation as our constant, okay? That's this term over here. So let me just get my highlighter out here. So the rule is our coefficient. That's this number by x. And our start is our constant, which is the number that's on the outside with no x. Okay? And in the graph, what you'll notice is that 220 is our where it's going to start or where it's going to cross the y-axis. We call that the y-intercept. Okay, and negative 72, our rule, is going to show up as our rate of change or our slope, okay, which mean the same thing. All right, so now let's go ahead and define some things for you here. So the slope-intercept form is y equals mx plus b. I think you've seen this last year. That's always for linear equations. We talked about what linear means. Linear means in a straight line, a constant rate of change. It's changing by 72 every time in this situation. The value of m is called the slope. The value of b is the y-intercept. So the m is the coefficient. That's our slope or our rate of change. And b, the constant, is our y-intercept or our start. Okay. So if I'm using some of our terms from the recursive, the slope is that rule, and that y-intercept is our start. Okay? Remember, y-intercept is where it crosses that y-axis. Okay? And then here's how I decided which variable to use. Okay? So our independent variable is always x. Oops. Our independent variable is always this x, okay? And our dependent is always our y. And how you have to do is you have to think about which value depends on the other. So in this case, we chose hours for our independent variable and distance for our dependent variable. So we chose hours and we chose distance. That's because the distance that you were away depended on the amount of hours that you were in the car or the van. So independent variable is a variable whose values affect another variable, and in a graph those are always on the horizontal axis or the x, sorry. And then the dependent variable is distance. That's the variable that depends on another one. In a graph those are always on the vertical axis, okay? And here's a little hint for you, okay? Any time that you have any measurement of time, hours, minutes, seconds, it's always going to be independent. So as a little hint to yourself, time is always independent, okay? Because time really doesn't depend on anything. Time just goes on as it always is, so time is always independent. It's always going to go along the x-axis, okay? All right, so I think you're ready to hopefully try a problem here. You're going to consider this scenario. Sam has burned 325 calories before he begins to swim for his workout. His swim will burn another 7.8 calories for every minute. Define the variables, so the x and the y, the independent, dependent, and write the equation in slope-intercept form to describe this relationship. As always, if you have questions, please fill out the question form on the website and make sure you bring those with you to class also so that we can discuss them before we get started with whatever activity I have planned and the focus problems later on.